Let us talk about this problem. We are given a number n. Our task is to do sum of first n natural numbers. If n is 2, then our output is going to be 3. 3 is sum of first two natural numbers, 1 and 2. 4, we need to return sum of first four natural numbers, 1, 2, 3, 4. So output is 1 plus 2, 3, 1 plus 2, 3, 3 plus 3, 6, 6 plus 4, 10. N is 5, sum of first 5 natural numbers, which is 15. So our output is 15. There exists a direct formula to solve this problem. If you are given a number n, you can simply write a function that returns n into n plus 1 by 2. You can simply write a one-line function to get the sum of first n natural numbers. The idea here is to solve this problem as an exercise for recursion. So please try writing a recursive code to return sum of first n natural numbers. When we solve a problem using recursion, we need to think in terms of solutions of smaller problems. Suppose I want to know the sum of n natural numbers. Can I use sum of smaller natural numbers, smaller number of natural numbers to get the sum of n natural number? The idea is simple. If you have sum of n minus 1 natural numbers, you can add n to it to get the sum of n natural numbers. So if I have sum of n minus 1 natural numbers, get sum n minus 1 is say available, my answer would be get sum n minus 1 plus n. So this is how this recursive code is going to work. We call get sum 4. Get sum 4 is going to call 4 plus get sum 3, right? Whatever get sum 3 returns, it's going to add 4 to it. Get sum 3 is going to call get sum 2 and add 3 to it. Get sum 2 is going to call get sum 1 and get sum 1 is going to call get sum 0. When get sum 0 is called, we cannot break this problem further into smaller problems because there can be 0 natural numbers, 1 natural number or 2 natural numbers, right? Not less than 0. So what happens when you have input as 0 natural numbers, your output is 0. And this becomes our base case. So when we are reducing a problem into smaller problem and smaller problem further into smaller problem, there comes a case where we cannot reduce the problem into smaller problems, and those cases are base cases. So 0 is explicitly handled here in this code. We write if n is equal to 0, our answer is 0. Sum of 0 natural numbers is 0. This is the code in Java. Now, how this execution flow happens? Get sum 4 calls 4 plus get sum 3, and then this calls this, and this calls this, and when get sum 0 is called, it returns 0, right? It falls into this base case and returns 0 immediately. When it returns 0, its caller is going to return 1 plus 0. So get sum 1 is going to return 1 plus 0, 1. And get sum 2 is going to return 2 plus 1, 3. So get sum 2 is going to return 3 to the caller. And caller is going to do 3 plus 3, 6. And it's going to return 6 to its caller. And this caller is going to return 4 plus 6, 10. So this function returns 10 to the main function. Let us now talk about time complexity and auxiliary space for this function. When you call this function for input n, it's going to make n plus 1 function calls, right? And every function call is going to do some constant amount of work. Some addition, some condition check, and then returning, which is all constant work. So we can say it's going to do theta n work, right? And there is a recurrence way also to find the time complexity of this program. We can say Tn equal to Tn minus 1 plus theta 1. This is also a way because when you call for n, it calls for n minus 1 and does constant amount of work. Now if you draw the recursion tree, you will have theta 1 work and there will be n plus 1 levels. So this way also you can say theta n time complexity. Now talking about the auxiliary space, see, recursion call stack is also an auxiliary space. So when you are calling for n, it's going to call for n minus 1 and this function is going to stay in the function call stack. And then when this function is called, this is going to stay in the function call stack and it's going to make a call for function get sum 2 and so on. So when you call get sum 0, these functions are there in the function call stack. They are waiting for their child functions to finish. So at a moment, you will have at most n plus 1 functions in the function call stack. And when will that happen? When the call for get sum 0 happens. when get some 0 comes here for an equal to 0 condition, at that moment you will have n plus 1 functions in the function called stack. And then the number of function would start reducing. Get some 0 will finish, then get some 1 will finish. So they'll become n, then n minus 1, then n minus 2 and so on. And ultimately there will be 0 functions in the function called stack. So we talk about the worst case. How many function calls are there at most at a moment? So we have n plus 1. So we can say theta n auxiliary space. So this function requires theta n auxiliary space for n plus 1 function calls in the function called stack, and this much time.